Today in this video from Jensen's lab, we're going to make an attempt to rewrite radio history. So we have a radio receiver on the workbench from 1921. This is the Colin B. Kennedy Type 110 model. And let's take a tour of the radio. You can look at all these knobs on here, and they have all kinds of weird names like coupling and filament and regeneration. This one down here is called the secondary condenser. But anyhow, these radios didn't actually have a frequency knob where you just simply dial in the frequency. You would adjust all these different parameters from the circuit and listen for a signal on the earphones. On this radio, we actually have a set of earphones connected, and they're hanging on the lamp here. Now, as far as frequency goes and what frequency we're dialing in, maybe what station we're nearing, I'm cheating. I have an oscilloscope connected to the radio along with a digital counter, and this is going to count the frequency. So if you open up the top of the radio, you see the vacuum tube. This radio has one vacuum tube in it. It's called a detector tube. There's a secret magic affiliated with this particular technology, this vacuum tube from 1921. We'll get to that in a minute. I'm going to connect the radio up to its battery power. I'm going to hook up the filament supply with that battery. You'll see the tube is now lit. Now, secondly, I'm going to hook up the plate voltage. The plate voltage for this particular tube runs at 45 volts, so this is a 45 volt battery. Now, I'm going to come over here to the oscilloscope and show you the oscilloscope as I hook up the battery. Yeah, the radio goes into oscillation, and our frequency is 1.388 megahertz. Nice oscillation. It's continuous wave. It's clean. And that's what it's supposed to look like. Okay, now getting back to the detector tube that was used in these 1921 receivers. Looks like a vacuum tube. No big deal there. Us old guys were used to seeing these vacuum tubes. They used to be in televisions and radios. There's something different about this one. These aren't actually vacuum tubes. This is some magical technology. This is an example of a UV200 tube, and it actually has a shot of argon in it, so it has argon gas. So this thing is ionizing, which is helping the conduction of the tube detect very, very low signals. The particular model UV200 tube, I've got 6 of them here. 6 dead puppies. Apparently these tubes didn't really make it into the 21st century. They all outgassed, or maybe the tungsten filaments stopped beaming electrons. But yeah, they're all dead. I haven't found a live one yet, but these tubes were upgraded to a detector tube that instead of argon, they placed a alkali vapor in them, and that was the number CX-300A tube. And there's a bunch of these around now, like on eBay and stuff, that are live, and they work very well. And that's what I'm using in this current video. But let's talk about that. There was also a tube number called a UV 200 tube, and that actually used a cesium vapor in it. It almost sounds radioactive, but these tubes actually had, maybe a low pressure shot of inert gas in them to help the tube ionize and detect signals. This detection process in a gas-filled tube like the UV 200 relies on ionization and subsequent gas amplification, which is fundamentally different from the operation of a normal vacuum tube that we're used to. Primary ionization, the incoming radio frequency signal acting as a form of ionizing radiation within the specific operating conditions of the tube, interacts with the gas vapor atoms. This interaction knocks off electrons from the gas atoms, creating positively charged ions and free electrons, known as ion pairs. But anyhow, this process seeked to add a greater amplification to the detection process. And if you actually run one of these radios, it's interesting how this works. I'm going to turn this one on and make a demonstration. Hook up my battery here. Let's see. I'm going to hook up the filament. Okay, the tube is running right now. The radio is running. It's running at 1.38 megahertz, and we're getting a clean sine wave. If we play with this sine wave, yeah, that's CW, continuous wave. No big deal. But, if I come over here and maybe adjust some of these knobs a little bit, maybe adjust this one down here, what we get on the display is a decreasing of the amplitude. If I turn the knob the other way, the amplitude increases. But then at that one certain point, it goes crazy. It actually breaks down into a like an oscillation process. If I adjust the time base and voltage, okay, whenever I increase the amplitude on the continuous wave, the signal breaks up into this crazy audio pulsing kind of a mode. And whenever it does, you can hear the audio on the earphones. But what is that audio pulsing mode? If I stretch it out, you can see the carrier wave at that 1.3 megahertz is actually inside that pulse, and then the pulse eventually dampens, and then it quenches to a flat line, and then it rises up again into a new pulse. Now the amplitude of this pulse is 2 to 3 times what the carrier wave was. So what we have is this crazy effect where the carrier wave is rising up, and the amplitude and the power in the system is too much for the detector tube to take. so the signal eventually dampens, and then it just flatlines to 0. And then the whole thing regenerates again once the tube recovers. And then the whole process happens again. It dampens and then goes to flatline. And this is the quenching period. And then the system regroups, and it regenerates the carrier wave into a new pulse. These pulses are happening somewhere around 4 to 5 kilohertz. And the pulsing can be heard in the earphones. But if we stretch out each pulse, we can see that the carrier wave exists inside of each pulse. So this effect, let's see, I'm gonna come over here and I'm gonna try to adjust the radio to get us back to CW. Whoa, that's getting bigger. And there's your CW appearing again. And that's the radio operating in its normal mode. But once again, if we increase the amplitude, the radio breaks into its pulsing state. What's interesting about this pulsing state is that being a gas vapor tube, and the tube is ionizing in this mode, something weird is happening. I'm gonna explore that over here. If we take our tri-field meter and set it on, I can get a focus here, set it on electrical field mode, and just bring our meter over to the detector tube in operation. There's no pronounced electrical field present, and at this point I don't even know why we're doing this. But we come over to the oscilloscope and we see that the radio is actually oscillating at 1.3 megahertz, and we're confirming that with just a regular continuous wave signal. No big deal. But when we adjust, I got stuff falling apart here. When we adjust the signal to go in its overdrive mode, bring up the amplitude up. Oh, it is now pulsing away. There's your individual pulses appearing. That crazy thing is just pulsing away because we're overdriving the detector tube. All of a sudden, if you look at the E-field meter, it's reading 300 volts per meter. If we move it around to actually catch the beam coming off of the detector tube, I mean, there's 900 volts per meter right there. The E field coming off this tube is phenomenal when it's pulsing. What does that mean? It's interesting. It's interesting. It's like the tube the radio just turned into a super regenerative effect, where you're placing the carrier wave inside of a pulse. And I wonder, when I started this video, I says that we're going to make an attempt to try to change radio history. I wonder if Edwin Armstrong's super regenerative radios were inspired by this effect. I even go on to wonder if the Rife Ray #1 was exactly this effect.